Hello and welcome to Dr. BT's Chemistry Essentials, A-Level Chemistry made easy. In this lesson we're going to be looking at catalysts for Year 1 A-Level Chemistry. So a catalyst has three components to its definition. First of all, it speeds up a rate of reaction. And it does this by providing an alternative pathway of lower activation energy. And you can imagine this as basically riding a bike over a hill. And the catalyst basically does the job of creating a tunnel that goes straight through the hill, therefore requiring less energy to overcome it. And the final part of the definition is that the catalyst itself does not get used up. Now we can link our analogy of a hill in terms of an energy profile for the reaction. So if we adapt this, if at the start of our hill is the enthalpy of the reactants, and imagine that the end of the hill, slightly different from our diagram, if we were just to increase the height of this flat area of grass here, up here, then we'll be showing an endothermic reaction, as shown by the energy level for products here, and our enthalpy change relative to the reactants is higher up, so we have a positive endothermic enthalpy change of reaction. Now, just like in our analogy, you have to go uphill in order to get onto the other side. With the reactants going to the products, you also have to go uphill and form the products. This is because you need enough energy to overcome the activation energy. That's the minimum amount of energy required for a successful collision. And so, those particles that can overcome this energy have the ability to turn into the products. Just like if you got to the top of the hill, you can go down to the other side. And so this is the uncatalyzed activation energy. If we add a catalyst to the reaction system, this will provide an alternative pathway of lower activation energy. For example, this curve here. And so this new energy expense is called the EA cat for catalyzed reaction. And this relates to a Boltzmann distribution curve, as the EA uncat is on this line, and then the catalyzed reaction will have a lower energy. And as these curves show the statistical probability of a particle with the energy, you can see it's more statistically probable, as the area is bigger, for particles to be colliding with energy greater than the activation energy of a catalyzed reaction versus one of an uncatalyzed reaction. If this diagram of Boltzmann distribution looks new or you're a bit confused by it, then be sure to watch the video on Boltzmann distribution and rates of reaction. So to summarize in terms of particles and collision theories, if we add a catalyst, then the energy required for particles to successfully collide is going to be less because we've lowered the activation energy. And so there are more successful collisions, i.e. those with the energy required, and so our overall rate of reaction increases. There are two different types or classes of catalysts. One is homogeneous catalysts, and the other one is heterogeneous catalysts. The homogeneous catalysis is one that's in the same physical phase as the reactants. So if the reactants are an aqueous solution, then your catalyst is also aqueous. On the other hand, a heterogeneous catalyst is one where they're in different phases. Often this could be that the catalyst is a solid and your reactants are either gases or liquids, and they adsorb onto the surface of that solid. An example of this is the nickel catalyst using the hydrogenation of alkenes. The nickel catalyst is solid, and then, for example, if you take the alkene ethene, that is a gas. And what happens is the alkene adsorbs onto the surface, so that when hydrogen also adsorbs onto the surface, we get the two reactants, hydrogen and the ethene, reacting together to form ethane. The formation of forces of attraction is called adsorption, not absorption. That's really key. Absorption means to go within the volume of a material. This is just making attractions to the surface of it. And once the two hydrogens have been added on, then the ethane diffuses away through a process called desorption. Other examples of heterogeneous catalysis is, for example, catalytic converters, which uses platinum, palladium, and rhodium alloys, and they basically oxidize and reduce different pollutants. So they oxidize carbon monoxide to carbon dioxide, and they reduce nitrogen oxide down to nitrogen gas. And so you can see here the carbon monoxide has converted into carbon dioxide, and the nitrogen monoxide has become nitrogen. These are much better, and whilst carbon dioxide is not a good pollutant because of the greenhouse gases, it's less toxic than carbon monoxide, which bonds irreversibly to iron and heme. And the nitrogen gas is inert, so this is an absolute ideal gas to be chucking out of the exhaust of a car. And another example that you might remember from GCSE is the use of the iron catalyst in the Harbour process, which takes nitrogen and hydrogen gas to form ammonia. And so we've got our iron solid catalyst, and nitrogen and hydrogen are both gases, as is the ammonia formed. Now, catalysts are very good for economic importance in industrial processes, and this is due to the fact that because they lower the temperature at which industrial processes need to occur at, they therefore reduce the energy demand which comes from the combustion of fossil fuels, and so you reduce the amount of CO2 produced because you're burning less fossil fuels, therefore linking to an increased sustainability of your industrial processes. So they're really key in industry. So that covers catalysts. I hope you found this lesson useful. If you have, please like the video and ensure you subscribe to the channel in order to get all your chemistry essentials.